All right, so we are live, and hello everyone. It was a while ago that we had our last YR webinar, and so yeah, YR webinars are finally back. And so as you know that we are going to have our global conference on 10th of December, and we also decided to organize those two webinars, so very valuable with very valuable guests. So the first one is going to happen today. So don't forget to register our conference, and so we are waiting for your papers as well. So soon the program and agenda will be announced. All right, so today we have a very valuable guest here, and Krystian Zieliński. And so, yeah, he's my former colleague, but forever friend. And so we did very cool stuff together with in our previous company. And so, yeah, it was pleasure to work with him. And so, yeah, we actually structured the things together from scratch, like from nothing, from zero to hero. Let's say we can call it like that. So I will just say few words. I will say few words about Krystian. And Krystian is right now working as a data scientist, and he has also a master degree from data engineering. And he's also teaching in WSP University, and then he works there also as a lecturer, and he teaches machine learning and data science. So previously, currently actually he's working at Invicta in R&D department. And so previously, like I said, we had a chance to work together in the financial crime domain. So where he developed tools to help to prevent the frauds. Currently, his focus is totally different than the financial crime. But you know, we are data scientists, and so for us, data is the most important thing. If we have good enough data, so things are pretty all right for us. And right now he's analyzing genetic data, searching for correlations with medical data, and his tools based on AI provide core functionalities in IVF. So now he will actually tell us more about, you know, the research studies in Invicta R&D department, and how he will tell us how we can use machine learning to deal with such actually very important and vital and such problems from the directly from the real life. Now, Krystian, floor is yours. And also, I would like to just mention one more thing before Krystian, I will pass the ball to you totally. So, dear audience, so we are excited again, like I said, and we are also encouraging you to ask your questions. So you can ask your questions on YouTube chat. So you can keep asking. So at the end, we will have Q&A session, and I will pick up your questions and then just pass them to Krystian. So please keep asking. And Krystian, floor is yours. Good luck.
Yeah, thank you. Thank you very much for the introduction, Ogun. So hello, everyone. My name is Krystian Zieliński. As Ogun said, I'm working currently in Invicta R&D department as data scientist. And actually, I would like to talk a bit about a project that we ran lately. The topic of today's lecture will be analyzing gene variants using machine learning, but the whole project, the whole topic that I'm going to speak today is way broader. So let's start. First thing first, a couple of things about the Invicta, very quick introduction. So Invicta is actually a chain of medical facilities, but we are like way more than that. We have our own laboratories, the genetic laboratories, and so on. So what's the advantage of that? We produce the data. We have the facility to produce the data that I could later analyze. So one of the projects that we had was focused on supporting doctors in IVF process. And thanks to this project, a tool called IO was created. So yeah, I will talk about this very tool today, from the scratch to the development and actually the production. So very quickly, just to make sure that everyone understands what was the goal of our study, let me talk briefly about the IVF procedure. First of all, the patient just fills the medical form relating to the medical history, all of the issues and so on. And with this form, he and she goes to a doctor, to a gynecologist who is specializing in fertility. And then the decision about whether or not to start IVF is made. I mean, this is very simplified version, of course. It's not like that. The ball can bounce between those steps multiple times. So just keep it in mind that this is like very simplified version. Yeah. So then step 3 and 4. So those steps were the actual goal of our study, because next, based on the medical history of a patient, laboratory results, and so on, gynecologist has to make a decision about the IVF protocols. I mean, currently we use 4 different IVF protocols, and depending on which will be chosen, the IVF procedure will look completely differently. So that's like a very huge decision to be made. After that, the patient goes for the visit on the first day of the stimulation, where the second very important decision is made about the dose of the gonadotropin. This is like a medicine that is being taken to stimulate the process. And then the step 4, 5, and 6. So after the stimulation phase, gynecologist collects the mature oocytes. We will call it M2. And at the end of the process, the healthy oocytes are fertilized, forming embryos. And one of those embryos is transferred into patient uterus. So this is how the process looks like, very simplified. So what we thought could help the doctor into those 2-step decision making. So decision about the protocol and decision about the gonadotropin doses. So we took the data, all of the medical data that we had in Invicta, and we gathered a lot of it. It was around 13,000 processes, I guess, something like that. And also, we added the genetic data because we have our own laboratory, so we could produce it. We trained models that would predict the number of M2s that will be produced at the very end of the IVF process, because it's like the more the better. Like the more M2s we will have, the more chances of getting the right embryo is. And after that, doctors checked the results, if those models are actually accurate or not, and if those results make sense. And the goal was to suggest the protocol and suggest the doses, the proper doses for each patient. So it will be like a targeted stimulation process. Okay, so couple of phases of this process. First of all, we had to analyze the data that we had. We had 2 data sets. As I said, the first one was only the medical processes, like the medical data. In the second one, we also had the genetic data available. It was kind of large data set because we had over 400 columns related to the medical processes, and basing on the experience and knowledge of our best gynecologists, we selected 17 subsets of features. So, for example, the most important hormonal levels, so HMH, and age of the patient, the USG results, and previous data if it was available. So if it was like a second process for a given patient, we knew what happened before. So how we train the models, the first models. We assumed that the prediction of M2 will be just an average M2 for the whole population. Then we added the subset of feature previously selected by doctors, and we checked if the performance of model would increase. And that's how we chose the best subset of medical data that went into the model. So that's actually the hormonal level, the patient age, previous process, the number of M2s from previous process, the polycystic ovary syndrome, and additional features like selected protocol when it was selected. So it would be at the phase 5, the fifth stage. And count of antral follicles on first day of the stimulation. The whole modeling was done in a light gradient boosted machine. So we used the 5-fold cross validation. You can see what were the parameters of the model, and use the Shapley values from the model SHAP to explain the model. And that was the thing that was very appreciated by the doctors, because we knew what was the impact of each feature for a model. So that itself was very important information that we got from this study. So that the AMH was the most important feature. It weighted the most, as opposed to, for example, age of a patient, which was thought before that might also be very important. Like from our study, it looks like that's not the case. So that was the modeling part. Okay, but yeah, cool. We have a model. Right now we know what to expect from a patient, let's say, but how to get from here to the suggestion of gonadotropin doses and suggestion of IVF protocol. So our approach was like that. We fitted the kernel range predictor with the prediction of the model and divided it into different protocols or doses in the later stages. And we checked what was the density of usage of each protocol for each prediction. And based on that, we fitted the kernel to predict the proper amount of M2s based on the prediction of model and based on the protocol or dose that actually was selected by a doctor. And thanks to that, we knew, for example, that the protocol short antagonist would behave rather worse for the patients where the expected M2s is quite high. So yeah, that was the idea and how we made it. So yeah, just once again about the Shapley values. This is very important that we can explain the impact of each feature on the model, but also the impact of each feature on each prediction that is made by the model, because we are talking about the patients, and it also gives the insight for doctors why the prediction value is as it is. So okay, we have quite high prediction of M2s, it's over 8. Okay, why? No, I can see that the AMH hormone is very high. So that's why it increased the number of M2s that we would expect to achieve for a given patient, and so on and so on. So having that in mind also very helps for doctors to understand what will happen in the process and why is that. And thanks to the fitting the kernel, we can see how the prediction for each dose would change. What was the gain to use different doses, and if our prediction was made on a sufficient number of data. Because let's say, for example, we would have a patient that we would predict that the number of M2s will be, let's say, around, I don't know, 50. So like very high amount. And in our data set, we didn't have such patient. Like that's quite impossible, let's say. So then the suggestion wouldn't be trustable because they wouldn't be based on actual patients. It would just be like an imagination. So that's also very important to know that those predictions are actually valid. Okay, so that was the phase one. One more thing, because I said the more M2s, the better, because then we will have more chances to get the right embryo. And that's just half of it true, because there is a situation that's called hyperstimulation, and it's defined as producing, let's say, more than 20 M2s, and it actually might be dangerous for a patient, and this is the state that we would rather not to be. So that's why we also have to keep in mind that, of course, the more the better, but too much of M2s might also be dangerous for a patient. So that's why we trained a completely different model. But the goal of this one was to calculate the probability of for the patient to end up with hyperstimulation. So that's why doctors not only have the data about which protocol is the most effective, but also they have the information about the probability of hyperstimulation. So if the probability is very high, the doctor rather won't prescribe the very high doses of gonadotropies, because it will just increase the probability, and it might be very, very risky. Okay, so right now we have both models based on medical data predicting the hyperstimulation, and we also have the suggestion of a path of IVF. The next step, and actually the main topic of today's speech, is adding the genetic data that would increase the accuracy of this model, the predicted accuracy of this model. So this is how the data looks like, basically. So this is what I saw when I analyzed the data. So I can see the chromosome position, the reference, and the variant, because we analyzed the variants. So long story short, it looks like that. We have our DNA, and it's very long. It has like multiple positions, and sometimes in one position there can be like different values, let's say. The reference and the alternative, the variant itself. And we checked which variants, but those are not anomalies. So this is very important. Those are just different variants. So we checked what variants may increase or decrease the probability of having high M2 for a patient. Why I showed those pictures? Yeah, we tested 16 selected genes. So this is the list. And we used for that, I mean, saying we, I'm not saying I didn't run those tests. This is the very good job of our laboratory. Yeah, we used NGS. What's impressive about that? Yeah, so those are the chips that are used in NGS. I have one with me. Actually, I'm not sure if you will see it. Probably not because of the light, but you can see the picture. So those are very small chips, and just one of it with one of it we can analyze more than 12 millions of locations. So it basically says up to 12 millions of variants in just one plate. So this is very efficient stuff. Yeah. So we had the data, we had the patients. So right now, how can we select the important variants? So yeah, that was kind of a trick, because analyzing the single variants didn't affect in any promising results. It seemed like the single variants are not sufficient to increase the accuracy of the model. So we spiced the things up a bit. We created 3 different completely separate paths of analyzing the gene variants. First one consisted of couple steps. So we created a ranking, the variant importance ranking, based on Boruta, Boruta-Shap, and Boruta trained on the data set with variants, but also with AMH, as it seemed like this is the most important correlator, predictor of M2s. And with this ranking, we selected top 20 variants, and based on those variants, we trained a self-organizing map and correspondent analysis. And we, just checked for genes combinations that would be kind of critical for given groups of patients. So that was the first path. The second path was a more common one, so just basing on the statistical importance. So he used the Uman-Whitney and Kolmogorov-Smirnov statistical test, and based on that, we selected the combination of variants that increased the predicted number of M2s and decreased the predicted number of M2s, statistically speaking, of course. And the third one was using the haploview. So it was actually suggested by people from laboratory, and based on 3 different rules, we selected the haplotypes. I will talk a bit more about those haplotypes later on. Yeah, so that was the first step. Then we trained the UMAP. This is the algorithm that also groups the similar observations together. Then we use this data into the decision tree, and then we, based on the path to a UMAP group, we selected the subset of variants that seemed most correlated with M2s. We checked all of those combinations together, and finally we got what we wanted. So the data set that consisted of medical data and genetic data that could be used to predict M2s and was more accurate, and it actually was. So let's jump into the first path, initial variant importance. Yeah, so that's how this ranking looked like. Each variant has its position assigned and the final score. Based on the final score, we selected top 20 variants. Later on, the correspondent analysis. For those who may not know, it's a very cool algorithm to plot on the same plot the features and the observations. So we used as one axis, those were the variants, and on the second axis we had the group of M2s. So basically M2s from 0 to 2, from 2 to 4, from 4 to 7, from 7 to 11, and so on. So basically 5 groups of M2s. And we could see that there are some variants that are more characteristic for a given group of M2. We were especially interested in those that are characteristic for the lowest and the highest groups of M2. So in this case, we had 4 different variants that were most characteristic for the group with the lowest M2. And actually, we explained over 80% of Interia. It was quite, it was unexpected, to be fair. I thought that the model will not be such a good representation of the data, but it actually managed to understand the correlations there. On the same data, we also trained the self-organizing map. This is also an algorithm for grouping, but it behaves way differently than the correspondent analysis. I won't go into the details of it, but basically what we can see in this plot. So each dot is actually a neuron, and in each neuron, we can say that we have assigned observations to a given neuron. The bigger neuron is, the more observation lay into the neuron. And again, we wanted to check if there are any characteristic variants for for patient groups of M2. So how we did that? To each neuron, the color actually indicates what was the fraction of observation from each group in this neuron. So we can see here, I'm especially talking about this yellow one. So this is the highest fraction of observations from the lowest group of M2 are actually they are laid into this neuron. So then when we knew that, we selected the most frequent variants that were in this node, and that's how we got our 6 variants that were characteristic for group with low M2 using self-organizing map. So this is like the first path. The whole process was very demanding when it comes to analyzing the data. I can tell you that. Yeah, so the second approach, way easier in my opinion, but also quite efficient. So we just calculated, the statistical value and p-values for each variant using 2 different alternatives of tests. So Uman-Whitney, so the amount of M2s in the group where the variant was absent would be higher or lower than in the group that there was found, the variant was found. And same for Kolmogorov-Smirnov test. And based on that, we created 2 different subsets of features. The first one, so those are the variants seemingly with a positive impact on M2. So statistically, those patients have higher M2 counts than the ones where those variants were not there, and patients with counts statistically lower. And we only included those variants that were selected by both of those methods, so both of the statistical tests. Yeah, quite easy. But this is actually a tricky one because previously we cared about the differences in M2. In the first approach, we grouped the patients based on the M2s. Here we analyzed the differences in distribution of M2 in each group. But here we didn't care at the amount of M2s at all. So what we actually cared was if those variants were nearby each other, and what were the combination of those variants, how frequent they were in the whole population. So this is completely different approach. Right now, we could say that we think that the variants that are placed nearby should actually be characteristic for a patient. And also, we assume that having the alternative here is the same as having the reference value. So basically, we checked what were the actual values on each place. So thanks to that, we have like very long chains of variants, and we can see what values should be in each position, considering all of the variants that are in a given chain, which we would call haplotype here. Yeah, we used 3 different methods for that, because there are different methods that search for the similarity of those variants. Yeah, and checked those haplotypes in our model. So out of over 300 haplotypes that were found using those methods, 3 of them actually showed very strong correlations with M2. So we ended up with 3 haplotypes, but as you can see, those are quite long haplotypes, and we found out that some of the places might not actually be important. Those might be just the noise that actually just happens to be between, let's say, those 2 that would be important for our analysis. So right now, how to remove them? Yeah, so we used the uniform manifold approximation and projection method. And with that, okay, how we did that? So right now we only care about the variants that are selected in given haplotype. So let's say we have 40 of variants. We create a data set out of the medical processes and those 40 variants. And we are grouping those processes using this method. And clearly we can see that there are a couple of separable groups here, but we would be probably the most interested in the biggest group. So the next step would be to assign the number of group to each observation that we have in our data set. And using just a simple decision tree, calculate the paths, basically create a classification model where the label of the model is the label of group in this method UMAP. Thanks to that, we can right now extract the quickest path to a neuron with the highest number of features. So in this path, we can see that almost all of the observations are in group 1, the first group, and this is this group that we are interested in. So right now we don't care about the 40 variants that we started with. We only care about 1, 2, 3, 4, 5, 6. The 6 variants that are actually important here. Yeah, so finally we have those variants. So how to decide which is the best, because we used three different methods. Well, we just checked for each combination of those variants how those combinations would reduce the RMSE of the model. And thanks to that, we can see that the combination of some variants and those three haplotypes that were selected reduce the RMSE by the largest amount. So it was 0.23. It actually concluded to around 7% of the model RMSE. So it's actually quite cool. When we spoke with biologists, they were expecting somewhere around this amount of results. So it's still fine. And moreover, those variants selected were actually treated as a very important one by SHAP. So especially the variant which was selected by SelfOrganizing map was decided as the third most important feature in the whole data set. So that's actually kind of nice. Yeah, I can see that it's already 40 minutes into the speech, so I will very quickly go to the next slides. Yeah, deep neural network rules, because the previous models were trained on using light GBM. Then we thought, okay, why not? Let's go with deep neural networks. And we can see that on the test data set, the comparison of neural networks and light GBM, you can see it itself, you know, for 4 different types of model, all of them actually benefited from using the neural networks, and by a quite large margin again. So finally, we ended up with RMSE around 3.10 on average. Yeah, and this is actually what we had in also like a side project that we run. So just, you know, heads up for you, if you analyze the genetic data, try the neural networks rather than tree-based algorithms. They work way better with it. Okay, so we have the model. What's next? Well, we created an API using Fast API that's connected to the PostgreSQL database. We Dockerized it and you know, created a couple of endpoints. Each endpoint basically was responsible for giving the information about the specified path of IVF for the patients. It looks kind of like that right now. For the front end, our software development team used Vue.js, for the backend Python, and this is the snips of a part that the model actually is being used. So we can see the impact on M2 prediction for each value. Also, the Shapley plot is also available for our doctors. It seemed like they would actually use that. And also in the table, the doctors can see the gonadotropin doses in this example, but for the protocol, it looks the same. And the prognosed M2 for each single gonadotropin dose. And, you know, doctor can see it, and, you know, basing on the hyperstimulation probability and prognosed M2, the gynecologist makes the decision about the doses. So yeah, it looks basic like that. Yeah, so thank you very much for all of the people that were involved in this project, because it looks like hell of a work from the data science perspective, but believe me, like it was just a tiny part of the whole project. There are many teams that contributed to that, and I would like to thank all of the people that were involved. I hope I didn't miss anyone here, but basically our R&D team, our IT team, our BMO, so this is the laboratories, DPO, so our software development team. We had the help from the University of Gdańsk. We had help from our doctors from our clinics. And also we were helped by the meme solutions team. So big thank you for all of the people that were involved. Like without you, it really wouldn't be possible to create such a great tool. Yeah, so thank you all for watching. I hope that the idea of analyzing the variant genes wasn't too overwhelming. I know that this is like a very complex thing to describe in 45 minutes. I hope at least you have right now the idea how complex it is, and also how the data science tools can be used in this process, and how the doctors can benefit from it. Yeah, you can just you can find us at our webpage, the CBR Invicta PL, and so on. You can see those links. I won't go into the details once again, and that's heads up for Wire Foundation. Thank you very much for having me here. I'm really glad that you also support such initiatives, that we have a space to talk about those topics, because it's very important to talk about it. Yeah, and thank you very much. Like always a pleasure to be with you guys, and I hope maybe when we will go with another projects, we will have another session. Yeah, thank you.
All right, so yeah, great, Krystian, and thanks a lot. And so for us also, it was a pleasure to have you here, and great presentation and a very good analysis, and actually end-to-end. You described the end-to-ends basically from zero to hero, right? So from basically digging into data just to basically having a end product. So it was very nice presentation, and thanks a lot for that. So we can also right now see very good comments from the audience as well on our YouTube chat, and there are also a few questions there. I would like to ask you those questions. And so the first question is like this. So it was regarding variable selection. And so in variable selection, this the approach or method was based on domain knowledge of gynecologists. So you mentioned this, and was there any consideration given to using RF as basis for picking variables and comparing that to the gynecologist suggestions? So this is a question.
Okay, so RF, I assume we are talking about the random forest, yeah?
Yes, yeah, I mean, I hope so. So
yeah.
RF and gradient boosted. So I think this is what our friends mentioned here.
Yeah. And for the genetic data, yeah?
Yeah.
Yeah, so actually we kind of did that because as you know, the Boruta and also Boruta SHAP, those are the algorithms that base on the random forest. Actually in Boruta SHAP we used XGBoost, because you can use different algorithm in the kernel, and based on the permutation importance, those methods just point out which variants are important or not. So this was actually our first approach. We just trained the Boruta and Boruta Shab for selecting the important variants, and then use those variants in our data set. But unfortunately, when those variants were used as a single feature, the impact of on the model was not too high. So that's why we went further with that and tried to find a specific combination of variants that might increase the accuracy of the model.
All right, so thanks for the answer. And there are like a few more questions on the chat. And so the one question is like this, so asked by Bartek Prushinovsky. Then he's asking, which field turned out to be more challenging when it comes to building successful ML models, financial crime or genetics?
Yeah. Hi, Bartek.
Very good question, actually.
Yeah. To be fair, I mean, in my opinion, genetics, and actually it's even hard to compare those two, because here the main process, the most difficult process here was to select important variants. So basically it all comes down to important features, and it was like I don't know, 3 months of a process just to select the important ones. Here we were kind of lucky because we had only 633 variants. I say only, it's still a lot. But out of those, finally, I think we finally selected around 18, something like that, like 3 different combinations, but overall total it was 18 different variants, combined properly. What was very fun, because what was the more challenging? Genetics for sure, but also it was way more fun to play with this data because we could try like a lot of different approaches, and it's still the field is still to be found. The best methods are still to be found in this field. So that's why we could actually play with this data. And in financial crime, you rather don't have such detailed data if you play with that. So this is the limitation. Like basically you hit the roof at the very end, because you can get only what you have from the data. And that's it. Here we could also like really squeeze this data and try to get the most of it. So yeah, I think that's it.
Cool. So thanks for the answer. So Pavel Kovalik asked you a few questions, and they are looking really cool questions. And so the first question from him is like this. I think you were mentioning about collecting data via some forms from the patient, and so his question is like this: that did you check somehow the forms filled by patients? So, as you know, people can put invalid data or like wrong data, or they wouldn't like to share what is correct.
Yeah.
So, and yeah, how would you deal with that? Also, this is another like a question and like a challenging topic.
Yeah, Paul, that's a good question, because we had a lot of concerns about the quality of the data. I mean, we were sure that the data that we are gathering in Invicta is properly gathered, because we have like a lot of steps where we validate it. But as you said, it's always tricky to analyze the data filled only by the patients. Actually, I mean, luckily enough, those data points were not selected as important ones. Maybe because they were filled poorly. I don't know. It might have happened. But we didn't put much attention there because, statistically speaking, at the very beginning of our process, those data points were not selected as important ones. We rather chose the medical tests data, the previous processes data, also the results of USG, which is run by us. So again, this is just the safer spot to create a machine learning model. Yeah.
Cool. I mean, it's actually good to hear that those variables were not found important ones by those metrics. So I mean, by those techniques, so which is good. So another question again from Pavel, and it's like this: that is this project live? I think there is another question. Maybe let's just answer this one. Is this project live? So I think he meant here if like end users can reach out and see some part of this project.
Yeah. Actually, it's on the production right now. I think the kickoff was like around 2 months ago, so it is available and accessible for our employees.
All right, cool. So he's also asking if there is some success rate for those tests, those approaches. So I mean, probably he meant here whether there is any like feedback from the real life. Okay, so we can check the accuracy and so on, or RMAC and so on, but how about comparing those predictions with the real like insights of the doctors or biologists and so on? So did you do something like that?
Yeah, actually we will. Right now is just too soon. The sample is just not enough because, as I said, it's just like 2 months, so we're still waiting to gather more data. Actually, we also are still in a process, making the tool more user-friendly and so on. So we are constantly on the talks with our doctors, and we are hearing what might be like another features that they would find useful in that. So the tool is working, but it also lives and it changes itself a bit still.
Yeah, sure. So maintenance.
But we will check it, and we will find if it actually helps with a number of successful pregnancy. Like that's the end goal, basically.
Okay, cool. So you will see actually on the way how it is or how much it is helping those decisions or those processes and so on, right?
Yep.
Okay, cool. Yeah, I think those are all of those questions from the chat. I have one question. So actually there is a huge effort here in terms of data science, and there are statistical tests and machine learning models and feature importance and hyperparameter optimizations as well. And also you mentioned about the neural networks. And so do you have any plans to go like to open source? Of course, not whole part of the project, but some part of it. I don't know, providing some part of related to DNM. This is actually hard to find right now regarding this genetic data. There are also a lot of state-of-the-art architectures on the literature regarding image processing and text processing and so on. And they are very well known, but is there any plan like this from your side to go at least with some part of the approach to open source and make some part of it open source actually. So to say.
Actually, this is a question I have not thought about. So yeah, you should be on the spot. I have no clue. We didn't spoke about it. Yeah, so maybe like that. We didn't spoke about it. I'm not saying yes. I'm not saying no. It's very tough right now to answer. However, I can say that we are currently working on a paper, the kind of huge paper about this topic, and there we will, share the knowledge and what we've done with this with a broader audience. So at least that.
Okay, cool. I mean, this is also part of open source, right?
Yeah.
So you are sharing also your approach and methodology and so on. Okay, I mean, what I can see, people are saying thank you and they're saying very nice presentation, very valuable. I definitely agree with them. So I think we can slowly close the session. And thank you so much, Krystian, for being with us today. It was really nice to listen this topic, and so also you dig into details and in terms of many topics. So thanks a lot once again.
Yeah, thank you. And pleasure is all mine. I really enjoyed this session.
Same here, and hope our audience also enjoyed. But what I can see from the comments, they enjoyed as well. All right, so everyone, thanks for watching and thanks for being with us today. So as I was mentioning that our webinars are back, and next week we're going to have a pleasure to host another webinar together with Dr. Ipek Güler, and then she will be also talking about some topics related to biostatistics. And so I would encourage you to join to this session as well. And then, as you know, that at 10th of December, so we will have our global YR conference. Unfortunately, again, this year it will be online. So hopefully next year we will be able to come back to on-site events, but you never know, but fingers crossed. And thanks a lot once again, Krystian, and thanks a lot for everybody who stayed with us and then listened us and then just contributed to the talk with the questions. And so see you soon, and bye-bye.
Bye.
Bye.